Turn on the computer.
Okay.
We don't have a dedicated computer for the badger, so the badger is installed on over here.
Okay.
So you just turn on the computer and wait for the computer. So I send you the menu.
Yes.
Did you read it?
I just give it a quick read. Yeah.
Yeah. So like I said, operation of the lasers are all the same. So today I'll show you the 532 laser. This is the most popular one.
Okay.
And if you need others, you just switch others on. I usually suggest if you don't know which laser you're using, you just start with the 532. And this is turn on, and the rest of the laser off.
Off, right.
So we just keep it for this one, it's on. And while we are waiting for that one, so we can start from this side. So this is the two spectrometer.
Okay.
We have 4 lasers that covers visible and IR infrared. So one is for visible, one is for infrared. So how to tell which spectrometer you should use? A simple way, you just look at the wavelengths. So for the shorter wavelengths, the 2, 488, 532, you use the spectrometer 1. In the software, sometimes they call it CCD1 or Raman CCD1. For 633 and 785, you use a 2.
Okay.
Okay, either called spectrometer 2 or Raman CCD2.
Okay.
So spectrometer, laser, spectrometer, there's no operation. It's always on, but it's not in working condition. Everything is controlled by the server and the software. Laser, the only operation is you turn it on, turn it off. This is the most important part because the laser is consumable in this case.
Okay.
So if you leave the laser on after you use, so your charge will based on the laser on time.
Oh, okay, I see.
Not the time you use the Microscope. So if you forget and the next day we may check, we may not check. But if we didn't check and you let it run for 48 hours, you will be charged. Your advisor will be charged for 48 hours. So before you leave, just make sure the lasers are off.
Okay.
Okay. The Microscope. This is called the laser shield. So it has 5 points, that's a magnetic, and it will match the 5 points on the stage. So it will stay in position by the magnetic force. Most of the time, users don't use this one because you need to, the objectives, we have 5. And I'll show you, it's also stated in the manual. Not all the objectives are usable for every sample. So we suggest you put a sample on the glass slide like this, 1 by 3 inch glass slide. This is a silicon wafer.
Okay.
This is my standard sample. This wafer is very simple. It's flat top with a big cross, etched cross in the middle. So we use that one as a feature to locate the surface. To load the sample is easy. So the tool rate had 6 positions. In the manual, we already said
mentioned
it's
5x.
position 1
Okay.
is 10 excellence for Raman. Position 2 is dark field lens,
50x.
so we don't use it.
Okay.
If you do Raman, you don't use it. Number 3 is 50x lens for Raman. Number 4 is 100x for Raman. So 1, 3, and 4 are 3 sets of lens for Raman with different magnification depending on your need.
Okay.
Number 5 is empty.
Enter.
Number 6 is also 50x for Raman. So the difference between 3 and 6, they both are 50x. The number 6 has a very long working distance. So this working distance is about 8 or 9 millimeter.
Okay.
So which means from the objective to your sample surface is about this distance. And number 3 lens, the distance is less than 1 millimeter. Number 4, 100x lens, less than 0.5 millimeter.
Okay.
So if you have anything like liquid, gel, powder, or non-even surface sample, you can only use number 1 and number 6.
Okay.
Because number 1, 10x lens, it also has 9 or 10 millimeter working distance. So you only have this type of sample. Flat surface, no spikes on the surface. And you can use number 1, number 3, number 4, and number 6. So you have 4 objective to choose from. But if you work with powder, liquid, or very viscous liquid, gel, any solid sample, not even surface, maybe has a slope or has like the surface is not smooth, you only use number 1 and number 6. Okay, so you still have 10x and 50x choice. But if you have silicon wafer like sample, very flat surface, you mount it to the glass slide flat. The reason, it depends on your sample size, because this size sample is comparable to that center hole. If you put this sample there, it might fall into the hole. So this is just to support your sample on the stage, so it won't fall into the hole. And the position of the hole is the center of the stage, so you can easily locate your sample to the center, right? And this two spring, most of the time we don't use it, because the stage itself, it only do X and Y move. It's never tilt, never rotate, never up, never down.
Okay.
So you don't worry about your sample there, it slide off. And also the move is very slow, so the moment of inertia won't like move and it won't just slide off. So you don't worry about that one. So most of the time we don't use this spring. But if you choose to use a spring, you must, these two springs are also magnetic,
Okay.
right? You put it on, and you can rotate. And you must make the two spring arms spread outward.
Okay.
Okay? Why? If you do this way, so I'll make it, try to put your sample, if you want to use these two springs to hold your glass slide, try to make your sample in the center of the glass slide. And in that case, number 1 lens, no problem. But if I move the number 2 in, you see this arm is very close.
Yes.
If you move it inward, it will touch the lens and damage it. So you either choose not using this one, so to let it spread outward like this. If you use, let it spread as far away as possible.
Okay.
So that requires you put a sample in the center of the glass slide.
Okay.
Okay, so now I put the number 1
So
lens.
do we get the glass here? I mean,
You can get it here, you can get it from your lab. You can bring everything. We have a glass slide there, but I don't have a glue here. It does not need a glue. You can just put your sample on the glass slide. But when you put it on and take it off, you
Just be
keep it
careful.
flat. Yeah, don't let it slide if it's pressure sample.
Okay, understood. Because my
Okay,
sample
this
is
one is fixed by glue, so it's up to you. So we have this glass slide. We have some simple ways to help you prepare sample. So this is the only one we supply. Of course, some pinwipes. And if you need some special support for your sample, you just prepare at your lab. And I'll show you what type of sample you have. This is a 1 by 3 inch glass slide. You can use a 1 by 1 inch glass slide. The hole is about 5 to 8 millimeter diameter. I'll suggest you use 2 times of the size.
Okay.
So 1 inch by 1 inch is good. Don't use anything smaller than that.
okay.
And the height of the sample, a few millimeter to like maybe half a centimeter, good. But if you have something like a few centimeter, that will be tricky. We never do the sample that high. If you have sample that one and try to chop the bottom off. If not usable. So I'll suggest that don't use anything higher than, let's say, 1 millimeter. Between 0.5 to 1, that already very dangerous. If below 5, you just come in to use it.
Okay.
Okay. So you might ask, so the stage only move X, Y, where the Z? Z is over here. So
Okay.
the whole head
Okay.
will move up and down. So this gives you kind of like a reversed operation. So if I said, okay, let's go down. So that means I move this one going down, and I'm moving my objective close to my sample. Okay. If I said, okay, so let's go move up, so that means I move my lens away from the sample. So this is like how you can focus your sample surface.
Right.
And this one, don't change it at all. They are not for the regular Raman, and including this one. On the head, you only have this wheel and this wheel to operate. And this, because we have 4 lasers, right? So depending on which laser you are using, you need to rotate this wheel. For one wheel should be empty. The other wheel should show the laser you want to use.
Okay.
Okay?
Okay.
For example, you want to use 532. This wheel is 532, this wheel is empty. Another example, you want to use 785.
Okay.
Okay? 75,
And
but
this
this
should
one,
be empty.
you must rotate until you see the empty.
Right.
Okay. So now, today we will use 532. Okay. So we rotate, rotate, rotate. So this is the direction you should rotate. You can move both directions, but we suggest that you just move this way.
Okay.
532, and this one
Should be empty. Right.
Okay.
Got it.
Okay, so now we turn on the computer, it's already maybe 5 minutes already. So while we are waiting, you need to come here.
Okay. Sorry.
So in the quick load place, we have a server, which is this one, the purple with the H. This is the server. You click on that, it shows you the status of the server.
Okay. Right.
So you don't do any operation here. You must check. After you start the computer, you see this page. You wait 3 to 5 minutes,
Okay.
and then you click on this H. These 6 items must be green checked. And if you wait not long enough for this spectral camera 1, spectral camera 2, they have the temperature, and sometimes you have a preferences next to the temperature. It says not stable. It's okay. You just don't collect the Raman. It means the temperature is not stable, but the hardware is good.
Okay.
Okay, so as long as there's a 6 green check, it will means the hardware is good. If you see not stable, doesn't matter, because we still need some time to bring up the software. This is the server. So all the microscopes, all the hardware, like instrument, if it's controlled by computer, it always has 2 levels of software. One is called server, one is called user interface. The server always run in the background. So in this case, you must check the server is good.
Okay.
It's up running. The 6 items must be green checked. And temperature is not stable, doesn't matter. We haven't started the user interface yet. Okay. The badger is installed here. So once you start a computer at any time, as long as you can run, so you just start the badger, log in, and enable it.
Okay.
Okay, log in now. We'll do the control 6. Okay, this is a user interface. Project 6 is data processing.
Okay.
So you find the control 6, you double click it, it will start. It contains 5 or 6 windows. One of the window is project 6. So you can run the project 6 alone for just the data processing.
Okay.
If you start the user interface by start the control 6, it also bring up the project 6. So you can collect data. Once you finish, you can go to the project 6 to process the data.
Okay.
Then you can go back to collect, process, collect, process. few windows, so it also checks to see everything is good, and it will show up. So I'll show you once it's fully up. It's fully up now, so it has a manual window. This is contains some like standard like a file operation view, like how you can save the file and read in the files. Okay, and we have control. This is one of the places you will use quite often when you collect the Raman. I'll go to details when we collect the Raman. So this is a message. So this message is just a communication of the software and the hardware want to tell the user something. So if something wrong, it will show up over here. And the video control, because this is a microscope, so you have option of take an image, and then on the image you can select a different place to collect Raman.
Okay.
Or you can collect a 2D area Raman. Every pixel it will collect a Raman. Okay. And this project manager, so this is a project 6. So every data you collected will list it from top to bottom. Over here, you just double click and you can look at the data.
Okay.
Okay, this video is a live video. So we use this joystick to control a lot of functions in this user interface. If you want to know, every button has a function. If you want to know more details, you go to this video control, you just go to the bottom area, additional. Here is a logo of this Xbox controller, right? And you click on that logo. So it tells you the function of each button. So
Right.
I'll show you the most useful ones. These two joystick, the left one, it controls the Z, only up and down.
Left one. Okay.
Left one. So which means this one, if you move left and right, no function,
Okay.
only up and down. And this is like a single operation. You move up, even you hold there, the Z will only move one step up and stop.
Oh, okay.
And you must move up, release, move up, release, move up, release, move up, release, kind of like a step by step moving. Same thing, move down, step by step. And if you hold this one, and then you hold this one up and down, so that will become continuous move.
Oh, okay.
So a little bit dangerous, because you, especially if you want to move down, you don't want to use continue for too long, because
Right.
it can crash on your sample.
Sample right.
More dangerous is the upper one. This is also continuous. It's called a turbo continuous.
It's more fast.
Much faster
Okay.
than the bottom one.
Okay.
So for this one, I'll suggest in the beginning, or
Don't use.
before you become an experienced user, try not to use this one.
Okay.
The right joystick, it controls the stage X, Y.
Okay.
So all four functions has a function.
Okay.
Direction has a function. Same thing, continuous, turbo continuous for this one. Otherwise, it only move one step.
Oh, got it.
So another very useful function is a Y. After you go to a different place of your sample, or if you switch the objectives and the brightness of the image, it will not do the automatic adjustment. So you must tell it to adjust. So which means the Y. The Y equals this button. You see auto brightness.
Okay.
So it said Y. So this one, you can auto brightness the image you can see over here. So right now, if you look at the sample, here you see illumination beam on the sample. It depends. Can you see that one? Right below is a
Yeah,
bright.
yes.
So for some sample you can see it, some sample you may not, because if the sample are not reflective, you may not see that one. So in the beginning, I will do this way to look at. So now, because of reflection, I can roughly see the cross. Okay, so now comes the important part. On the microscope, there's two manual operations you must remember. One, the objective lens you must rotate to select. Second, the laser, you must manually rotate the wheel to select the laser.
Right.
After you've done that one, and in the software, you must tell the software which laser you selected and which object you selected. The software won't detect. So for the objective, you must go to the video control. Here's the drop-down list. It lists the 6 objectives. It's match the 6 positions on the turret.
Okay.
So we are using the 10x lens at position 1. So I just click the 10x lens, and right now it's on 100x lens in the software. So it just asks you to confirm, do you really want to switch to 10x lens? You just said, oh yes, finish. So it switched to 10x lens. And now I can use this one. I can use continue. So you see, I move X, Y, and you can see the image is moving. And I just find the feature, I try to center it. So that probably, and then I also use Z up and down. In this case, we try to don't be picky at this stage, but just try our best to focus on sample surface. Okay, so now comes the question. Because this one is a standard calibration sample, so we put an etching cross in the middle. But for silicon sample surface, many times we have this dirt. A lot of times you will see sample surface like this. You don't have feature. So then how do you focus on the sample surface?
Okay.
Okay, so that's a question, and difficult also. So over here we have 2 operations. Listen, you may not need it all the time,
Okay.
but this aperture it only controls how much light illuminated on the sample. Most of the time, you don't need to change it. So right now it's kind of like in the middle, and you don't need it, because if you look at there, I rotate this wheel, you see brighter and darker, brighter and darker, right?
Right.
And you don't need to change this one. Or sometimes we just make it smallest and we can auto balance. So that also works.
Okay.
So the smallest aperture, the illumination is already good enough. Okay. And this is labeled F, so this means field stop. It's also an aperture. Right now it's fully open. But if you rotate it and make it smaller, and you will start to see the aperture. It's a polygon shape. Okay. And this aperture is a reference to help you focus on the sample surface.
Okay.
Yeah, for example, if I move
Oh.
a lot away from sample surface, it's autofocus.
Right.
And the aperture is also autofocus. So at any time you load your sample, you move to 10x lens, and you just found, oh, I don't see any feature. Based on your knowledge of your sample, you might know, oh, my sample is very flat, silicon surface, we don't have much etched feature, so it might be called featureless. So you just insert this aperture.
Okay.
All you need to do at this stage now is you just move up and down to make the edge of the aperture sharp. If you see the blurry dot, sometimes if it's a lot of ways, so you don't see the shape of the aperture. But right now you don't know whether you should move up to focus on a sample, or you should move down to focus on a sample.
Right.
So one thing you can do a quick check is you just look at over here.
Okay.
And like I said, this number 1 lens is about 9 millimeter working distance. And how much distance you think is now?
Maybe less than that.
It's more than that.
Okay. Yeah.
You
it's
must
like a
lower your
centimeter,
head.
right,
You
right.
must lower your head and perpendicular to that distance, and you just do estimate. It's definitely more than 1 centimeter.
1 centimeter. Right.
Okay, so I should move down.
Move down. Yeah.
Okay, so if you decide, if you cannot see whether you should move up or you should move down, you should always move up.
Okay.
It's safe, right?
Yeah.
And for this one, don't worry. You move up and you look at this bright dot, and if you see it's even more blurry, so that means you probably should move down.
Right.
Okay. So right now I can see it's move down, so I just much longer than the 9 mm, so I just move down. So I use continue, not a turbo. So I don't do it for a long time, so I just do maybe 1-2 seconds and stop, and I watch that one. Looks like the dot is become bigger and the edge is start to get a little bit
Sharp.
like a sharp, and so that means you are doing the right direction. So you just do move down, just for 1 or 2 seconds, and move down, and move down even sharper. So that's good. Move down and move down, and once you see roughly the shape is very clear, although the edge is still blurry, but the shape is very clear. You don't do the continuous anymore. You just do this one, and. Let's see, sharp, sharp, sharp. I continue move down. It started to become blurry. Then I should move up. So this is a way how you focus on sample. You just move up and down, and until you see a sharp edge. And once you see that, you just remove it.
Okay.
Okay.
By this.
Yeah, you can see the logo.
Yes.
Bigger, smaller.
Okay.
You won't miss. And auto balance bright. Okay, so now we only use this as reference to focus on sample. Are we really focus on the sample? So we can go to the center to check. Yeah, the feature is quite sharp. So which means this works. Okay, so once you, that's not too much you can do with the 10x, because it's not a big magnification. Second, the Raman signal also not strong with 10x. So you can either switch to the number 3 or number 4 if you have very flat sample, or the number 6 if you have powder or other non-flat sample. So I'll show you to use number 2. Is it very scary, right?
Right.
It might scratch. All the lens, their focus are calibrated. They're not perfect, but once you focus the sample surface with 1, you won't worry about the rest of the lens to hit on the sample.
Right.
And number 3, also very scary, it's very close. And then number 4 is the shortest. Looks like it's already touched, but it's okay. So I'll show you the 100x lens. And because the 100x lens gives you the best Raman signal. And remember, manually switch here, manually switch there.
Right.
1, 2, 3, 4. The number 4 lens, 100x, click, and finish. So now we have 100x. The focus is calibrated but not perfect. At this stage, you still need to work on that, either move down or move up to focus on the feature. And the brightness is not comfortable, so you just do the Y and move up, move down, and focus on the feature, and do the Y. So because the crossing area is not an even surface, so I want to move. You see that red circle in the image?
Right.
That is a reference, shows where the laser locate.
Okay.
Okay. So I just put a flat surface on the sample surface, and now I'm ready to collect the Raman. Okay. So this is a microscope operation. So at this stage, you can switch between 10x to any of the lens you want to collect your final Raman. Switch between those two. At the 10, you have a bigger view area, easier to locate your area interest, and easier to roughly focus the sample. And then you switch to either 50x or 100x to zoom in, so this will give you a better Raman signal. Okay, so let's work on the Raman. So remember I said Raman, we have a laser selection, and based on which laser you select, you must tell the microscope which spectrometer you need to use. So in the video control, we have the laser. So over here, you have to select which laser you're using. So 532. And based on the laser you're using, you need to go to the control. And here it's called Raman CCD1. You go to the drop down and Raman. So you have CCD1, CCD2. So 532, which?
CCD1.
CCD1. Okay, it's already at CCD1, so we don't need to switch. right?
Okay.
It's already at CCD1.
Oh, okay, okay.
You can switch to CCD2. Just wait. It takes time. So we upgrade the Microscope from manual operation to automatic, like motorized.
Mm-hmm.
But this motorized operation take times.
Mm-hmm.
So you switch something, you must be patient.
Wait.
And until it's finished and the status bar disappears, so that means your operation is finished. And we can go back to the Raman CCD1. Yeah, for your experiment, I usually suggest you do the CCD first,
Mm-hmm.
and then you go to the laser and choose the right laser.
Okay.
Okay, and below the laser, this number is the power of the laser.
Okay.
So this microscope is used. It's called a true power. So if you use any other Raman before, not from this company, sometimes you just say, hey, I want to use 5% of laser,
Mhm.
10% of laser. Even for confocal, sometimes they give you this type of value, right?
Mm-hmm.
But if you publish, someone will ask, oh, what's the 5% means?
Mm-hmm.
What's the real power of that 5%? So you have to convert, right? This one just to give you the real number. So that value over here, the unit is milliwatts,
Milliwatt.
and there's always a range.
Okay.
I would suggest that for all the lasers, never use anything larger than 20 milliwatts.
Okay.
Some laser, like a 532, I think a 633 and a 785, all of them can go at least over 40, I think, milliwatts. But that's very, very tricky because most of the sample at the 20 milliwatts, that's already very, very large energy. And for silicon, you don't worry too much because it won't damage your sample. But for some soft matter, like a biology sample, if you use anything like a larger than 5 milliwatts, it will then burn your sample right away. Okay. So the maximum for all the lasers is somewhere around 40, 50 milliwatts. And during the experiment, I suggest that you keep it below 20.
Mm-hmm.
In case you need one, you just increase step by step, like each step, like 5 milliwatts. And if you input a value that is over the upper limit, it won't go there. It just stay at the maximum value. For example, 633, I think the maximum value is 43 or 44 or something. If you input 60, it won't go to 60.
Mm-hmm.
It just go to 44 and stay there. So in that case, you will know what the value of the maximum value you will get. So that's why I suggest try not to use over 20. Okay.
Can you please tell me the significance of high value, or what is the advantage of
Better signal.
hmm?
Better signal.
better signal?
Yeah. Raman is a very weak signal. Even we have the best Raman, probably the best Raman sample is a silicon. It gives you very sharp peak, a single peak. But for most of the other samples, you will get a very, very weak signal. Raman is a weak emission. Okay?
Okay.
So now you understand the value, right?
Okay.
Yes.
So the more the power, it's getting the signal is better, but
You get more signal. I will
Okay.
not say better.
Okay.
I won't say better. You just get more signal. The more counts in your peak.
okay. And but the danger is that it might harm the sample.
Yes.
Okay.
Yeah.
So what do you suggest for silicon wafer?
I don't have any suggestion.
Okay.
You try it.
Okay, you just recommended
Yeah.
don't use
Raman
over 20.
Is different from for other instrument. Most instrument you don't need to do any homework. You just come in and somebody show you do it. But a Raman, you cannot just come in and put your sample and start experiment
Mm-hmm.
without knowing anything about Raman, without knowing anything about your sample.
Mm-hmm.
You must do a lot of homework
Okay.
because this is spectrum. So you must know what spectra you are expecting. And this spectra is from which compound. And you need to find the standard spectra from the literature or from the database, or from similar samples that are published by others, published by yourself, published by your lab. And you have an idea of what type of spectra and which peak you are looking for.
Okay.
And then you come in and you do the experiment. Otherwise, you put a sample in, you won't benefit from that. Raman is different. You need to do a lot of homework. You also need to know why the sample give you the Raman. And for each standard, I don't know the semiconductor. The only semiconductor I know is silicon, silicon crystal, not silicon oxide. I'll show you what the silicon you are looking for, if it's a pure silicon crystal or pure silicon wafer. But other than that, I don't know much about semiconductor. You must do your own homework. Okay, so now we have the image, and this is a live, and you can go over here and you can take an image. So now you will have image data in the data tree. Okay. Every data you collected with this software, it always gives you two items in the data tree. The first one is a real image. Okay. You double click, it gives the image. See, it's the same as this one. The second one is a text file. It's a header of this image file. It just saved separately.
Okay.
Nowadays, I don't know why they do this one. Probably more like organization. Nowadays, for example, the TIFF file, they already have its own header. It's within the same file.
Okay.
So, but this way, this is a true data, this is a header file. The header file is always a text, and it contains all the parameters that you use to collect this data. Okay. If you want to repeat, just open this one, set Microscope to this condition, and you can take the same image.
Okay.
Okay, let's keep this image open. Okay, so once you have this image, so if you want to move just a very small distance on the sample, you can use this one, of course. So you just do this way, this way, this way, but you see every step, it has step size. For example, if you want to go exactly to this center of the cross, we may not achieve that one with just this one, you see? It's always like a little bit off, right? So you can use this function. It's called move sample to mouse position. You activate, it becomes red, and you just go to anywhere you want to move, and it's centered, right? During the Raman, the Microscope will be in dark field, dark imaging field, which means you won't see anything over here. It's just dark. So if you want to move, so this image is not only an image, it's every pixel of this image is also contains coordinate of the stage. So if you activate this function, you can also click on the image.
Oh.
It will move there. Okay, click on the image. So now I want it to move here. Remember to stop it. Why? Because if you keep this on and you accidentally click on the image, or click even this black, you click on anywhere in this black while the Raman is taking, it moves. So this is dangerous. So you must, you don't use it, you turn it off.
Okay.
And now we are ready for the Raman. So 532 and the laser power, I usually use 20 for the demo sample. And on the control, we used to set up spectrometer parameter over here, but the new software will give it to this additional. And over here, and you click on that, it gives you an additional window. So I already put it here. So this is for spectral 1, and it's a parameter. You have two parameters you want to select. One is called a greeting. So for CCD1, we have 3 greeting. You see 300, 1800, 2400.
Right.
And the grating, it determines the energy resolution. So the Raman spectrum, the full Raman is from 0 to 4000 wave number. Okay. For 300 grating, it will do the data collection every 3 wave number per data point, give you the Raman spectrum. Okay. For the 1800 grating, it will do every 1 wave number per data point. For the 2400 grating, it will do every half wave number per data point. So now the question is why I always use the highest energy resolution, why we should use a lower energy resolution, because the full spectra you collected with different grating are different. The lowest resolution with 300 grating, you will get a full spectra, 0 to 4000, with 532 laser. 1800 grating, it only gives you about 900 wave number range. Okay, 2400 will give you about 600 wave number range. And now the question you will ask, okay, you only tells me if I use the 2400 grating, I get 600 Raman range. Okay, where is the 600? From 0 to 600, or from 100 to 700, or from 500 to 1100.
Right.
That will be determined by the second parameter in this page. It's called the center wave number. So I will use 300 grating, so it will give me 0 to 4000. And I will put the center wave number at 2000. So that will give me 0 to 4000.
Right.
If I put at 1000, I will get minus 1000 to 3000. And our spectrum does not have the anti-Stokes shift. Okay, so every wave number should be positive. So if you show the negative 1000 range, you won't get anything, it's just flat. Okay, so we put this center of the wave number 2000. Okay,
Okay.
that's for 532. Set up spectrometer. Okay, so we are now good. So the next step is we want to test, because when the laser are really focused on the sample surface, you will get the best Raman.
Right.
We already focus on the surface, but it's based on the video image. Whether the laser is focused or not, or perfect focus or not, maybe not. Maybe just a slight off. So we have to use a live Raman collection mechanism to tune the focus
Okay.
to maximize the Raman signal.
Okay.
Before we start the Raman, we go to the server first and check these two CCD. They should be around minus 60 degrees Celsius, and you don't see the preferences not stable as it shows now. So you don't see anything not stable, right? So we are ready for the Raman. So I just click on the oscilloscope. You see, it becomes dark field, right? And it will show just the wait.
Why did you
Wait.
click just oscilloscope?
Okay. And this is a live Raman. You can see it's alive. Okay.
Why did you click just before?
I'll explain this and I'll go back to show you. Okay. So now it's roughly from 0 to close to 4000
Okay.
range. For the silicon, it has a silicon bond. The Raman of that bond is at 519 wave number. Very strong signal. And because this is an old sample, so the surface is already oxidized a little bit. So you have silicon oxide peak is around 950, which is, you see, very small. And whether this is the best peak or not, we don't know.
Okay.
Right? So I just use focus up and down to maximize my signal. Okay, so you see my signal goes up, and in the Raman spectrum, you can always scale the X and the Y using this auto scale.
Okay.
So the scale means if you auto scale the Y, so it will use minimum value and the maximum value and show it in the graph, right?
Okay.
And auto scale X means it will use all 4,000 range to show it.
Mm-hmm.
But if you move your mouse into the spectrum and you stop somewhere and you use the center rule to roll it,
Mm-hmm.
okay, it will use the current Y position at the center to manually scale your sample, right? So if you want to tune the size of your peak to be bigger and smaller,
Mm-hmm.
I suggest you just manually tune it, make the peak half of this display.
Okay.
Okay? But don't put your mouse here, because if you put your mouse here, it will use this center to scale up and scale above and below this line.
Oh, okay.
And you will lose your bottom line.
Mm-hmm.
Okay, you show the bottom line and put it a little bit lower the bottom line, and then you scale it up and down and make the peak like in the half of this place, and then you can do the up and down to better scale. So it goes up and it's still going up. So I just scale down and goes up and up. And so if you go over,
Mm-hmm.
and it will start to drop. So this same thing, you up and down, and keep the maximized signal. So this is a 519. If you move your mouse over here, you'll see here the y-axis is sorry. The
529.
x-axis is a 529. So it's hard to do it perfectly. Now it's 520.
Mm-hmm.
Okay?
Right.
And over here is about around the 950. So that's a silicon oxide peak. And this big sharp peak is a silicon peak.
Okay.
And we already make this peak the best.
Okay.
And also remember, because the laser might drift by itself,
Mm-hmm.
so the alignment might be off.
Mhm.
Especially for 532 laser, it drifts. And it does not have the constant speed. Sometimes after 3 days, it's still really good. Sometimes only after 1 day, it may drift off. So if you work with your sample, let's say for 5 minutes,
Mhm.
and you don't get a good signal, what I suggest is you just take off your sample and put it on the silicon sample. Or every time you come in here, you just put on silicon sample and use 532
Mm-hmm.
to check if your 532 is your is a laser you plan to use. And the baseline is always around 680 counts.
Mm-hmm.
Okay, for 532 laser with the CCD1,
Mm-hmm.
right? And right now the peak is 2000.
Mm.
So minus 680, so you will get 1,300 counts for the peak, which is really good.
Okay.
So for the interest peak, I always suggest for your interest peak, at least you will get 100 counts. 100 counts.
I mean, you mean
get
that?
that?
You mean the difference?
I think it's the difference.
Hmm?
I just say your interest peak.
Peak. Oh, okay.
Yeah, I didn't mention any
I mean,
difference.
here it's above 2000, right?
Yeah.
Peak.
Okay, so I understand what your means difference. Because the background is not at zero when you collect data,
Mhm.
right? So it's 680.
Mm-hmm.
So 100 counts for the peak, which means your peak must be at 780
Okay,
or
understood.
larger. Okay, that's not called difference. That's just called the peak size. And your background is not zero, so you just do the calculation yourself.
Mm-hmm.
Do a quick calculation.
Mm-hmm.
And it's not a sharp cut. You got a 99. Should I do anything? This is not a good. Versus 101. They both are good.
Mm-hmm.
Okay. Yeah. Don't be picky. And it's not a sharp cut. You got 80. Okay. You got a 10. Of course, not okay.
Mm-hmm.
Okay.
Understood.
So in the beginning, before you become experienced, I always suggest that you come in, you work with the silicon, this standard silicon sample, and you can get a good peak with the 532 laser, 20 milliwatts, and remember, so we got the 1300 count. So when the laser drift off, so of course your peak will drop. So if the peak count goes below, let's say 400, 300 counts for this peak, so that means the laser drifted too much. I need to do the alignment, and you don't touch the alignment, so you can find me. I'll do the alignment. Every other day I will check the alignment. So in 1 week I will at least check twice of the 532 laser alignment. All other lasers are really stable. I check it like every 2 weeks, so it's really stable. But only 532 is drift. But every week I will check at least twice. But when you come in, you just do some experiment with your sample. You don't get any good data. You put on the sample, the peak is still low, so that means it requires alignment. So you just find me to do it. So which means after this week, I will not available for about 3 weeks. So even after this training, you can only use it this week by yourself, between 9 to 5. And if you want to continue use it, you can only use it after February 13th.
Okay.
Because if you understand it, you just tell me.
I mean, is this because I'm new?
Yes.
Okay. But the guy, another postdoc in our lab.
Which lab are you from? And we can close this window. So now you ask, how do you start the oscilloscope? So in the oscilloscope, you have this logo, so minus plus. You click the plus, it gives you all the operation. And for the oscilloscope, you have only one parameter you can play with, the integration time. So it means how long the laser will shoot on the sample and last for a certain amount of time for you to collect the Raman. This spectrometer is very sensitive. You see, I only use 0.05 second to collect. So I already get 1300 counts.
Okay.
So that's very quick collection. So if you want to do the oscilloscope, you just do start the oscilloscope.
Okay.
And you must manually tell it to stop it.
Okay.
And oscilloscope will not save. So you see over the data place, there's no oscilloscope save. Once you're happy with the oscilloscope, so you want to collect a single spectrum over this place, right? So you just go down the control and you find a single spectrum. You click on the plus button, so it shows all the operations for the single spectrum. For the single spectrum, you have two parameters you want to change. One is the integration time. So you play with oscilloscope. You can change the laser power. You can change the integration time, and you just balance it, and you can get a good signal. So you don't want to use too long for the integration because your collection will not be quick enough. And you don't want too short, and your background has a lot of noise, so it covers your signal. And so that's a balance of integration time and laser power when you work with oscilloscope. So once you get a good parameter with oscilloscope, you can just copy this integration time to the single spectrum over here.
Okay.
So no matter what the default value is set, so I'm really good with 0.05 second with oscilloscope, so I put it there. The second parameter for single spectrum is called accumulation. So this is a little bit confusing. So you are not really doing the accumulation, you are doing the averaging. So the number you put it here is, I use 0.05 second to collect one spectrum. And accumulation 10 means I collected 10 times. I got 10 spectrum, and I average the spectrum, and I give you the final one. why we do the accumulation, or means averaging. So in the digital signal processing, if you do the averaging, it's a good way to smooth the background, which means to squeeze the noise signal. So how much the noise are being flattened.
Mm-hmm.
So it is the root square of the accumulation.
Mm-hmm.
Right? So if you do 100 times, so the average background will be shrunk to 1/10 of the single collection. Okay? 10 is the minimum one I always suggest. Even for silicon sample, maybe one-time collection is good enough, but we do 10. So 10 is one I always suggest. It's a minimum. Depending on the sample, you can increase it. But for your sample, you said you have silicon wafer, so 10 probably good enough for your silicon wafer.
Okay.
If not good, you can increase it, but try not to decrease it.
Okay.
So now we have this 2 parameter set. I just click on the acquire single spectra. But because I want to show you something, so I just turn this one to 50.
Mm-hmm.
And I'll do the single spectrum. And during the collection, you will see 2 spectras. One is oscilloscope, one is the spectra so far, and over here, it said how much is already fitting, 50. Okay, done. You see that? No?
I missed it.
2 spectra, one is here, one is here, and look at over here.
Mhm.
See this one?
Mhm.
You see this one?
Mm-hmm.
This
Okay, 50.
50, and if I maintain it at 10, I don't even have time to show you. Even the 50, first time you didn't catch it, right?
Mm-hmm.
So I go back to 10. So during the collection, you will see 2 spectrums.
Okay.
One spectra is called hardware spectra. So this is oscilloscope.
Okay.
And another spectra is called the spectra with a serial number.
Mm-hmm.
So this is the data you are collecting.
Okay.
So this is also a live update. I collected 50 times. And every time I collect a single spectra, it will update in this window.
Okay.
And this is accumulated so far.
Mm-hmm.
So for every spectra it collected, it will average with the previously collected signal.
I see.
So if you collect 1, it shows you 1. If you collect 2 spectra, it's average of 2. If you collect 10, it's average of 10.
Mhm.
It shows them until the collection finished. This is average of 50
Okay.
and show up. So you don't need it, you can close all of them. And now I collected twice, so I have spectra 1, spectra 2.
Mm-hmm.
So this is the default number name of the data. Go back to the control. The first one called sample names. You can random call it silicon,
Mm-hmm.
right? So with the given name, because you don't give any name, so before the spectra there's empty.
Mhm.
But if you give a name, so they use this given name as a prefix and use this one to follow the given name.
Okay.
Okay, we can do one more time. Single spectra 10 times. Finish.
Mm-hmm.
Now you have silicon / spectra 003.
Mm-hmm.
Okay? The serial number is always added every time you collect a new one. Okay, so that's pretty much how you collect Raman signal. You go to different area, and you go to new place. I always suggest you start the oscilloscope, and you just do a quick check, and whether the signal is the best or not. So move to the half, bring down, bring up. Yeah, it's still the maximum. And I'll stop it, and I'll collect the single spectrum. See? And done. Okay, so now I have a 004.
Right.
And you go to another place, and you can collect normal spectrum. Okay.
Hmm.
Okay, so this is how you collect data. After you got a long list of spectra 001 to like maybe 011, 012, and now you go back and you want to show in the publication or your presentation, you have this image, and you just want to show, oh, I have spectra 1, I collected somewhere. I have spectra 2, I collected somewhere. You don't want to tell people you collected somewhere. You want to tell people I collected exactly here. So, but you don't remember. Most of the time you don't remember 1, 2, 3, 4, 5, 6 where you exactly collected.
Correct.
So you just find the spectra that you want to show where you collected. You hold the spectra with the left key and you drag it. Forget this window. You just drag it into the image anywhere.
Okay.
And you drop. So now it's at show position.
Oh.
So this red cross center is where you collected the 1. 2, I didn't move, so it's the same position. So 3, drag and drop and show. Oh, 3 also in
3
this
also.
position. 4, drag, drop and show. So now this is the 4. 5, drag, drop and show position. And this is the 5. Now I add, because the 3 and the 1 they are same position, so the 3 should be blue, but it overlapped with the red. Once you put a bunch of cross, you also forget what the green means. Don't remember. So you just right-click the image and you see the transform drawing. It shows you the red is 001, the blue is 003, the green is 4, and the cyan is 5.
Okay.
Okay, if you don't like the color, you just go there and you can change the color. You can change the width. So the cross is a very thin line. You can change it even. You have only one level down to make it even thinner, or you can even make it thicker of the lines. Okay, so now I shows where you collect data, and for example, if you finish your experiment, you have a lot of data over here. You go to files, and you just save project as. This will save a single file. It's called a project file.
Okay.
And it contains all the data listed over here. And where to save the data? So on this local disk, local computer, we have a data D, and that's a user. So under this user, please find your advisor's name over here.
Okay.
If you cannot find it, likely you are the first one from your advisor's lab doing Raman here. Can you find your advisor?
Yeah. Yes.
What?
This Bruce Kim.
Bruce King? Okay. Go to Bruce King, and we have, I don't know whose data is that, and you put your folder under your advisor folder. And under your folder, do whatever you want.
Okay.
Okay? Different subfolder of subfolders, it's all up to you.
Okay.
Okay? And you give a name for this project. And it is saved as a WIP file. It's called a WITec project file. And this project file can only be opened by project 6.
Okay.
Yeah, I'll cancel this one with this software. The software, I have 2 copies of license, so I installed 1 copy over here. I also installed 1 copy in the main facility, the data processing computer.
Okay.
And also on the data processing computer, it's called a Recon PC, reconstruction computer, Recon PC. There also has a user folder on that computer.
Okay.
And I mounted that folder as an internet drive disk Z over here. So some users just like to save the data directly to this one. It's okay. But if you save it to there, you must be on your own to keep the data. Because I only back up data of this disk.
Okay.
So what I suggest is you save your data in the local disk, and then you copy your data to this user too. It's same thing. you just find Blue Skin Lab and put your data over here. Okay, and then you go back to the main facility, open the data processing computer, you find the user folder, and you will find your data. So now you have two places to save your data. So for the facility, we have certain responsibility to keep the data for a certain amount of time. So I only back up data on this disk.
Okay.
If you directly save your data on this one, you are on your own. Okay. So that's how you save the data as one single project file. But let's see, for this spectrum, let's work with the image first. For this image, you want to do some presentation, and you can right click and export. You have two ways to save this image. One is called bitmap to file, original bitmap to file. The difference is original, the bitmap to file means whatever displayed in this window, it will save. The cross marker, the scale bar, they all saved in the image. Okay? If you do the original bitmap to file, it only saves the image. Scale bar, the cross are not saved in the image. You can save both, and if you don't like this scale bar, don't like this cross, you can in the original save the image and you draw yourself. Okay, so that's how you deal with the image file. And for the spectral file, you just double click and you show the spectral, you right click, and you can export the bitmap to file. So it will save this spectral into an image file.
Okay.
And the format of the image is some standard one, so you can choose yourself. PNG, TIFF, JPEG, some popular one and some not popular one, but you can choose yourself. And because this is spectrum, so you just say, I don't want to show directly like this. I have my own software. I know MATLAB. I know Origin. I know Excel. So I want to draw myself. I don't want the software to draw for me. This software to draw for me. So you right click and export. You do the ask2 to file. This will give you a text file with two columns. The first one is X. The second one is Y.
Okay.
And you just port it to any graphic software that you are familiar with to draw the software, to draw the spectrum. You can also do some processing like a smoothing, remove background, and deconvolution. Because this data process software provided by the manufacturer, they are really simple and they don't have much advanced function. But this project 6 also contains some simple data processing, so I'll show you here. So let's open this one. And for this one, remember, when we left the mouse, hold and drag, and we see some functions over here, right? And so I'll show you maybe 3 simple data processing. The first one is called CRR. Okay. So I just drag my sample, go to this window, and I drop it there. So now it shows the CRR. And for any action, it shows this one will usually shows 2 spectrum. One is red, one is blue. And right now, the red and the blue are perfectly overlapped, so you only see the blue. Okay. And CRR means cosmic ray removal. So we may have some contamination rays that from somewhere, like in the universe, and it's collected by the spectrometer. So this software will do some simulation and find the cosmic ray and remove it. But for this spectrum, we don't collect any. So the spectra are the same. So the red one is the input spectra, which is spectra 001. And the blue one is after the cosmic ray, reverse side. The blue one is the input, which is the raw data of this one. The red one is after the data processing, it shows the red one. And we don't have any ray removed, so they are overlapped. So we just do the extract. So which means extract the red spectrum and save it here as a single one. It's a processed one. We already do so, but we have a next step. So I just do the extract. The next step is I want to remove the background. So background subtraction. And now it also show the spectrum and action, and now you see it's extracted, and the data had the same name as this one, but it's labeled this is CR removed. Okay. Okay. So for background subtraction, there's a couple of ways to do it with different algorithms. I'm not familiar with the rest of the algorithm. I'm only familiar with the shape. So this is most of the time people use it to smooth the background. Oh, sorry, not smooth it, to remove the background. So in this case, oh yeah, so the red one is always the input and the blue one is always the output.
Mm-hmm.
Okay, but then the background removal case, if you don't do the subtract preview, so the blue one will be the simulated background with the algorithm you selected. So let's just focus on this area, because other areas there's no background, there's no peaks, right?
Mm-hmm.
So for the X, you want to scale it. You just hold the Control K and use the center wheel. So now you can scale the X and make it bigger. And now we can make it bigger. Now we can see the background a little bit better. And we use the shape. So this is the shape size. You can you click on the shape size. You can input a number, or you can use up or down to make the shape size smaller. So now watch the blue line. If I make the shape size smaller, you see the background start to cut into the peaks, which is wrong, right?
Mm-hmm.
And you can make it bigger, so it starts to become flat. This is just based on your observation, so you just want to make it flat, not too flat, away from the background, and also it does not cut into the peaks.
Mm-hmm.
So normally in the 100 to 200 range of the shape size, it's good for most of the peaks. Okay. So somewhere around here, the smooth. And if you're happy, you just do the extract and the next step. So the next step, okay, so yeah, we can just do extract. So now we have CR removed and subtract the background. If we do this one, oh, they remove. Oh, in this version, they don't have the useful function within this software. You just go to smooth, and also they have 3 algorithm to do the smooth. Average is most easy one, easy to understand and also easy to use. So it's like a nearest 3 data point to do the smoothing. And the red one is the input, which means this data. The blue one is output, is after the smoothing. And if you're happy, you just do the extract. So now your data, from one data, you extract 3 times, so you got 3 data, same name, it's just a different processing. Okay. And after you do the processing, you still want to continue save it, because if you save the project file before and you don't save it now, all the processed data are not saved in the project file. In the end, you are about to finish, so you can save one more time of the project file.
Right.
So that is the most important raw data you must finish. You must save. Like right click, this image you right click and save it bitmap, you can do it. You forget, doesn't matter. You come back and you load the project file. You can do it one more time.
Mm-hmm.
As long as you have the raw data, you can do all the processing I just showed you.
Mm-hmm.
Okay, yeah, that's pretty much what you do with Raman. You go to different places and you just collect data, the single spectrum.
Thank you so much.
Okay.